Okay, so it is about 15 past the hour. I would say let's continue. And Timo, you wanted to run a poll. You want to go ahead?
Yeah, I can do that. So I hope all of you played along, and I would like you to signal whether you got ParaView to show you the solution and the animation. And if yes, click the more and then the thumbs up button inside the Zoom participants window. And if you were not able to do it, click on the thumbs down button in the participants window. So that we get some feedback and know that we're not talking into the void. You might need to click on participant list to see it. At least that's what I had to do.
So I see a few thumbs up work appearing, some thumbs down as well.
Some checkboxes. So I see 1, 2, 3, 4 or so no's. We will have some time today to help with getting things to run. You can either type in the chat now, we're trying to help you over time, or there's the opportunity after the talks today to talk to us.
Okay, so it looks like, at least for the majority of those who left an opinion here, it seems to work. And yeah, like Timo says, we'll try to address this at a later time. There's time after this presentation where we can look at individual error messages and things like this. Timo, did you get your feedback?
The only comment I saw is some people are still downloading the virtual machine, but I haven't gotten any specific questions that we should tackle at this point.
Okay.
There's one question on opening ParaView.
Okay.
Maybe, yeah, a quick comment on that. So if you open a terminal and type ParaView, enter, and you don't see ParaView opening, then we will likely have to look into that after the session. Because I cannot immediately come up with a reason why that cannot work inside the virtual machine. So if it doesn't work, then please let us know after the session and we will look into it.
Yeah, so let's postpone this until after the session, and let's talk about how Aspect works, maybe internally, but in particular how you interact with Aspect. So Timo already mentioned this, that Aspect is fundamentally a command line tool, but there of course has to be a way to describe the details of the simulation that you want to run. So you know, what's the geometry, what's the medium, what's the model that you're trying to simulate. So conceptually, when you try to describe a simulation, then in our case, the problem that we want to solve is a partial differential equation. So the partial differential equation in this case is fundamentally a force balance, like what forces act on material, and then maybe other equations that describe something like it is incompressible, or maybe it is compressible with a certain compressibility and so on and so forth. So these are all partial differential equations, and in order to describe a complete model, you have to say, well, which specifically is the equation? Then in these equations, there are typically coefficients. So coefficient could be, let's say, the density or the viscosity or the thermal conductivity. And you have to say which ones of these are dependent and independent variables. So for example, you could say that the density is independent if you have an incompressible material. But if it is a compressible model, then the density actually depends on things like the temperature and the pressure. You also have to describe the initial state of the model. So how does the Earth look like as you start your simulation, and you have to describe boundary conditions. And these are sort of the 5 big pieces that you somehow have to describe. That's the mathematical description of the model. And then, of course, the mathematical description is an infinite dimensional problem. A partial differential equation has a solution where the velocity, pressure, and temperature, for example, depends on the points or all of the locations in the Earth. There's infinitely many of these locations. That's too many for a computer. We have to discretize this, and we have to make it finite dimensional. That's what the finite element method does. And so the next piece that you have to describe is the mesh and the finite element choices on which you want to solve. And then finally, so you're running the simulation, and presumably you're doing this because you want to do something with the simulation. You want to evaluate the heat flux, or maybe you want to output at every time step or at periodic, every few time steps, how the solution looks like. So all of this is what we call post-processing, doing something with the simulation or with the solution that you computed. So that's the last part that you have to somehow describe to aspect. And all of these things are done in an input file. We sometimes call it the parameter file, and there's typically it has an ending .prm. And so what I want to do in the next 20 or so minutes is to walk you through how these input files look like. So conceptually, if you think about how to describe all of this, you have to think about how aspect looks like. So aspect fundamentally has a core, that's the simulator, and there are model setup things that go into it. So these would be the initial and boundary conditions and a bunch of other things. There is the mesh refinement in the box on the left. There's the material model on the box on the right. And then the results of the simulator go into post-processors. And you already see that there are errors going both ways, from simulator to material model and from simulator to the adaptive mesh refinement. That's because the mesh can change over time in response to how the solution looks like. And the material model is a description, for example, of the viscosity that appears in a model, but the viscosity might depend on the temperature and the pressure. And so it is also something that depends on the current state of the simulator. So in more detail, if you want to break this down, then the model description would be initial conditions, boundary conditions, the geometry, the gravity model that we use. The material model would involve the density, the thermal expansibility, the viscosity, and so on and so forth. The post-processors might be visualization, depth averaging, statistics, heat flux, and all of these other things that you might want to compute. And then the core fundamentally is a Stokes solver. So the equations that describe how the metal flows, but also how, let's say, you can describe tectonic processes on long time scales with the Stokes equation. The output of the Stokes equation is a pressure field and a velocity field. And then other things that we simulate in aspect is the temperature equation and something that we call the composition equation. So the composition fundamentally is, I think originally we thought of it as chemical composition. So say the fraction of material consisting of this particular mineral or that particular mineral. But over time, we have made this more general, and compositions are basically any other quantity that you would like to advect along with the velocity field. So it might also be grain sizes, or let's say, well, melt maybe not, but let's say the volatile concentration and things like this. So what we're going to talk about in this tutorial today is the things that I highlight in red. So it's how do you set up initial conditions, how do you set up boundary conditions, how do you set up geometry. The gravity, actually, I think we're not going to talk about, but it follows the same scheme. The material model maybe will be discussed in more detail in the coming days, and then how you post-process the solution. So do something with it. So, like I mentioned, all of these pieces, all of the inputs that describe what aspect is doing or should be doing are described in an input parameter file, .prm file. And then what you will find is that these input files are hierarchical. So things that belong together are grouped into subsections, and subsections can themselves have subsections again. These parameter files are clear text. You can edit them with any text editor you want, and they can be, and as a matter of fact, probably should be documented. So there's if you put a hashtag at the top of a line, then the rest of the line will be ignored. And it's good practice, like any other programming file, any other input file, you should document it to explain what you're doing. So here's an example. If you open the input file for this particular tutorial with LeafPad, Timo already showed how to do this, then these input files look like this. So there is, in particular, a comment right at the top. So these first two lines are comments. And then the format of this is always set, and then there's the name of a parameter, equals, and the value. So in this case, dimension equals 2, so we're running a 2-dimensional simulation. If you set it to 3, then you're going to run a 3-dimensional simulation. Similarly, if we set use years in output instead of seconds to true, that means that internally Aspect is going to run everything in MKS units, so in meter, kilogram, seconds units, but it can use years whenever you want to interface, let's say, so it writes the current time to the screen and to the visualization files in years, because that is just the unit that we are more used to. Similarly, in this case, the end time is interpreted in years. So in this case, we're running for 50 billion years. That doesn't make sense, of course, but for this particular simulation, it does. And similarly, down here is an example of a subsection. So that's the introduction of a subsection that describes the geometry model, and I'm going to show you more examples of this later. So this is just the general structure of how you describe all of these simulations to Aspect. So there are a lot of parameters. And if you ever wanted to know what they all do, there are two ways how you can do it. So one is you go to the manual. And so the manual has a long description of every single parameter. But then you can also look at this in a web browser. So if you go to the web address that's listed here, and I have this open somewhere, I just need to find it. So here, so if you go to the address listed here, you're going to end up on this website here. And let me make this a little bit larger. So it lists all of the parameters. So for example, let me find one, set end time. Okay, so and it lists the default, which is in this case 5.69 times 10 to the 300. And then in square brackets, it tells you also what is the format that you can use for this particular parameter. So it is a double precision number, a floating point number, and the end time can be between max double and plus max double. So these are the smallest the most negative and the most positive floating point number. If you click on this plus, it's actually going to tell you more about this. So let me close this one. It says the end time of the simulation. The default value is a number, so that when converted from years to seconds, it is approximately equal to the largest number represented by floating point arithmetic. For all practical purposes, this equals infinity. Units, year, if the use year in outputs instead of seconds parameter is set, seconds otherwise. So you can find all of these parameters. You can also search for things here. So initial temperature. So let's say I wanted to know something more about the initial temperature field. You will see that, well, it filters everything where initial temperature appears, like here, for example. This is maybe the section that I was mostly interested in, initial temperature model. So there are ways how you can find all of these parameters. I should tell you, so let me clear this again. So if you go to initial temperature, for example, I'm going to talk about this in a minute, but I want to show you another resource. So if you look at the initial temperature model, there's a parameter here. If you click on this, it's going to explain to you what can be there. There is a lot of text here. And it's pretty much unreadable because it contains formulas and because it is not formatted. So this website is good if you just want to sort of filter and find the simple parameters. But if you wanted to look really at what all of this is, then you would want to go to the manual. So the manual looks like this. I should go to page 1. So this is the front page of the manual, okay? And in this manual, there is a section called runtime input parameters. So it starts at page 291 and it ends at page 542. So there's 250 pages of parameter descriptions. And so let's find the temperature, the initial temperature model here. So it's alphabetically sorted. So if I want to find the initial temperature model, then this is the place where you can find the same information as in on the website, but with better formatting. So for example, if I make this a little bit larger here, so the list of model names, this was this giant block of text that you just saw. So in particular, it says the following initial temperature models are available. Okay, S40 RDS perturbation. And then there's sort of a text that describes what this is. Then S Savani perturbation. And then there's a text that describes this with references and formulas and so on and so forth, right? So this is the place where you can find all of the same information about each individual parameter that Aspect understands in more detail with better formatting. There's also, at the very end, an index of runtime parameter entries. So all of the parameters that you can find in input parameter files are listed here again. And in particular, so here it's just a flat list, but you can also have this sorted into subsections. And you see that there are behind some of these multiple page numbers. So what happens here is that each one of these page numbers corresponds to one place in the manual where this particular parameter is used. So for example, boundary temperature model, box, bottom temperature. So that's in the subsection boundary temperature model, in the subsection model box, in the subsection bottom temperature. This parameter is used in these 6 different places. And what often happens is that these are individual cookbooks or examples where a parameter is used. So if you ever wonder about, well, can I see an example where a parameter is used? This is the place where you find this sort of information. So let me go back to this here. So these are the resources where you can find information about these parameters. And then, so let's look at some of these in detail. So at the top of the input file were sort of global parameters that are not in a subsection. For example, the dimension, whether to input and output years in seconds or time in years or in seconds, the end time and the output directory. So in the input file that we're going to use in a few minutes, these appear on lines 3, 8, 9, and 10. Okay, and I should mention, if you're not familiar with this, so this syntax 3E10, this is how computers, or how in computers we often represent floating point numbers. It means 3 times 10 to the 10, right? So it is the 3 times, and then this is the exponent 10, so 10 to the 10. Similarly, if I had 2 times 10 to the 3, I would write this as 2E3. Okay, so these are the global parameters, and then let's look at other things. So the geometry model. So you might want to run things in a global sphere, for example, if you're interested in a global simulation, or maybe you just want to set up something similar in the box geometry. So for the tutorial today, we want to run something in a simple box. And how does this look? So we want to run it in a rectangular box in particular. So we want the height of this to be 3,000 kilometers and the width of this 4,200 kilometers. And that's because that matches a widely used benchmark that was defined, I think, in the 1990s. That's the origin of these sizes. And the way you do this is you go into the subsection geometry model, and you say that the model name, so the particular plugin, the particular geometry that you want to use is called box. And then in a subsection that is named the same way as the model, you set the x extends to 4.2e6, so that's 4.2 million. That's 4,200 kilometers. Remember, we work in meters, in kilograms and seconds. And the y extent, so the height in this case is 3 million, so 3,000 kilometers. Similarly, let's talk about the initial temperature. So the initial temperature field, you saw that already in the visualization that Timo showed you earlier, is sort of this bump over on the right. So it is hot at the bottom and it is cold at the top, so we have an unstable layering. And then we want to perturb this a little bit by making it hot over on the left and cold on the right, so that we get this sort of circular convection pattern here, okay? And you can describe this in terms of a formula. So the formula is shown in the middle of the page here. It's not particularly intuitive. That just happens to be how it was chosen in this benchmark. And the point I want to make is that in this case, we describe the initial temperature in terms of a function. And there are many other ways how you could describe the initial temperature, but let us choose a function, okay? So we go into the subsection initial temperature model. We set the kind of, the way in which we describe the initial temperature is by describing it as a function, and then we go into the subsection function where we say that the variables we use are x and y. There are constants, namely p equals this, l equals this, d equals, and so on and so forth. And then the function expression itself, so that's the t of x and y, is given by this particular formula that you see at the bottom there. And you see that you can use cosines and sines. In there, you can use the coefficients that you have defined, or the constants that you have defined in line 90. So this is one way how you can define an initial temperature. And in the tutorials that you're going to see over the next few days, you will see that there are many more ways how you can define an initial temperature field. So a common way, for example, would be to say, well, you start with an adiabatic temperature, and then you overlay something else a perturbation. That perturbation can come from a file that you read, or it can be another temperature profile, or it can be from many other sources. So there are many different ways, not just the simple ones that you're going to see today. The temperature at the boundary. So in this case, so we have a box. A box has 4 sides in 2D that are labeled as left, right, bottom, and top. And what we would like to do is we would like to prescribe the temperature to be 3600 Kelvin at the bottom, 273 at the top, and at the left and the right, we want to describe this as an insulated boundary. So there is no heat flux across the left and the right boundaries. And so the way we represent all of this is that we go into the section boundary temperature model, and we say that there are fixed boundary. So for the top and the bottom boundary, we prescribe these as fixed boundaries where the temperature is fixed. Okay. The bottom temperature is described as 3600. And the top temperature is described as 273 Kelvin, okay? And so you see that we don't say anything about the left and the right boundary. That's because if you don't say anything at all, then the boundary is assumed to be insulated. So it's no heat flux. Next, we have to describe what the velocity is. Again, for all 4 boundaries, we have to say what kind of boundary this is as far as the velocity is concerned. And there are many different ways how you can prescribe what the velocity should be at the boundary. So either you can say what the velocity is as you can say that the velocity should be, for example, let's say the top boundary should be described by a G-plates model, where you describe what the velocity at every point is as a function of space, as a function of time. Or you could say it is simply 0 at a certain boundary. Or you can say that you want to prescribe tractions. So tractions would be like you prescribe the force that drives the velocity along a certain edge. Or you could say it is a free slip boundary. So a free slip boundary is, you say no forces act other than those forces to make sure that the velocity does not cross the boundary. So the velocity can be tangential to the boundary, but we don't say whether it is large or whether it is small. That is something that the flow model should figure out itself, depending on the forces that act in the interior of the domain. So in this case, the forces that act in the interior of the domain is simply the buoyancy forces that come from a non-uniform temperature distribution. And when we say free slip, we say it's that the flow cannot leave the domain, but other than that, it can be whatever it wants to be. And the way we describe this in aspect is that we go into the boundary velocity model section, and we say that there are no boundaries that are 0 velocities. And for all left, right, top, and bottom, we say that the flow is tangential. Okay, so that describes the model. We have to say how we discretize the model, so how we come up with a finite dimensional representation of it. And in this case, we're just simply going to use a uniform mesh. So we have the 3,000 by 4,200 kilometer domain. And we start with just one cell, one big cell. If you refine one big cell 3 times, so the first time you replace it by 4 by splitting it vertically and horizontally. If you do it twice, you're going to get 4 times 4, or 16 cells. Okay. If you do it 3 times, then you're going to get 64 cells, or 8 by 8 cells. Okay. And similarly, if you refine 4 or 5 times, then you're going to get 16 by 16 or 32 by 32 cells. So how do you do this? You say you go into the subsection mesh refinement, and you set initial global refinement. That would be either 3, 4, 5 in the examples that are shown in the pictures. And then you can, there are many more parameters in this model or in this section that you could set, but we're going to say that there is no initial adaptive refinement, and then also we never refine between one time step and another. So if we set these values to 0, then we get exactly this mesh, and it's going to stay that mesh for the entire time of the simulation. Okay, and finally, we have to say what we want to do with the simulation once it is computed. So in this case, what we would like to do is we would like to compute statistics on heat flux and other things, heat flux across the boundary, for example. We also want to visualize the output, and then we have to specify, or we can specify certain properties of how exactly these the visualization should happen. So let's look at this. So we go into this post-process subsection. List of post-processors is a list of things that should happen at every time step. So for example, we want to compute velocity statistics, things like the average velocity, maybe the maximum, the minimum velocity in different parts of the domain. We want to compute similar statistics for the temperature. We want to compute statistics of the heat flux. So that is something that happens that we're going to compute for every part of the boundary. We want to run visualization at the end of each time step. We want to do some particles and some basic statistics. Whatever these things are, you can look this up in the manual or on the website, for example. And so for the details of the visualization, that again is in the subsection, we say that we want to have output every 10 million years, for example. Okay. We want to output this in BTU file format. So Aspect can output in many different file formats depending on which program you want to use for visualization. But for ParaView, for example, BTU is the appropriate file format. And then you can say what output variables you want to have. So in particular, it's always going to output the pressure, the velocity, and the temperature. But you can output many other things. So you can output material properties. So it would also output the viscosity, the thermal conductivity, many other things, for example. All of this would end up in the output file. And similarly, for the particles that we're going to use to visualize the flow field in a different way, you have to specify how many particles you want. So in this case, we want 1,000 particles that are randomly distributed by default. We want to output the particle information every 10 million years. And again, we want to output it in BTU format. So one of the things that you're going to find quite frequently is that, let me click back here while I talk. What you're going to find quite frequently is that you copy paste or that you type the name of a parameter into your input file, and that you have a typo in here, that you misspelled a word or a letter. And one of the things that's very useful in, I think, all aspects of computing, but certainly as far as input files of Aspect are concerned, is to learn to read error messages. So here's an example where Aspect starts to run and then shows you an error message. And learn to carefully read error messages, because it really helps you to understand what's going on. So what it says here is in line 1 of well, a certain file. So in this case, the file name is not provided, but then it says no entry was named output directory was declared in the current subsection. So Aspect is trying to read an input file and is confused about the fact that it doesn't know anything about an entry with name output directory. And of course, if you read carefully, there's the R missing here. So you will find this quite frequently, that you write an input file and you run Aspect with it, and it's going to give you error messages. Take the time to learn to actually read error messages, because they really help you, right? So in this case, in line 1, the error appears. Maybe I'll show you this later in a real world example, but the point really is read error messages. They help you find where the problem is. Okay, so with this, I think what we should do is just run a particular tutorial program or a tutorial input file. And so Timo has already shown you how to run this. I would like to talk a little bit about the background of this example file first to illustrate what we're trying to do here, and let's say why we set up this particular tutorial. So what this tutorial does, and you've seen this already when I talked about the parameters, it is a box that is cooled from above and heated from below. So you can think of this as a pot of water, for example. And what happens in these cases, obviously, is that convection starts and is going to transport heat from the heated bottom to the cooled top. So you're going to get a convection pattern going in this pot, in this box. And the point of this tutorial program or this tutorial input file is based on a benchmark that was defined in the 1990s. And the background of this is fundamentally this. So if you had a less viscous fluid, you would expect that there is a more vigorous convection happening. And that means that more heat is transported convectively. And that's sort of a simplified view of this because fundamentally it is not actually really the viscosity that matters. So if you think about a box full of honey, for example, if this box is just a millimeter by a millimeter by a millimeter, then even if you had a temperature difference of 100 Kelvin between the bottom and the top, then you're probably not going to get convection simply because honey on length scales of 1 millimeter is still a very viscous fluid. But if you had a cubic kilometer of honey, you might actually get convection happening. So that's because on the length scale of a kilometer, the viscosity of honey might not actually be large, whereas on a length scale of 1 millimeter, the viscosity of honey is large. So what I'm trying to say there is that viscosity always has to be considered relative to some sort of length scale. Similarly, if you had a cubic kilometer of honey, but a temperature difference of 0.1 Kelvin, you might not get convection. But if you had a temperature difference of 100 Kelvin, you might get convection. So whether or not you get convection happening also depends on the temperature difference between the bottom and the top. And all of this can be represented in a unitless number, a dimensionless number that's called the Rayleigh number. And it is given by the product of the density, the amount of the magnitude of gravity, the thermal expansion coefficient, the temperature difference between the bottom and the top, the third power of the size of the domain divided by the viscosity and divided by the thermal convection coefficient. So this whole thing, this big expression here turns out to have no physical units. It's a dimensionless number, and it tells you something about whether convection is dominant. So if the Rayleigh number is large, then convection is dominant, and if the Rayleigh number is small, then diffusion is dominant, or in other words, convection doesn't happen. So with this, then we can rephrase this statement in the following way. So we can say if you had a fluid and a domain and a temperature difference for which the Rayleigh number is large, then you would get more vigorous convection and more heat being transported. And heat transport, we're going to measure this through the Nusselt number, which in this case is simply proportional to the surface heat flux. So how much heat is being transported through the top and the bottom surfaces. So there is a known empirical relationship. I don't think that there's a proof that this is so, but we have good evidence that within a certain range of Rayleigh numbers, the heat flux is proportional to the Rayleigh number to the power of 1/3. And I looked this up a couple of days ago, and that's actually not quite right, because for the parameters that we're going to choose, the Rayleigh number is lower, and it turns out that for that, in that range, maybe the Rayleigh number the heat flux should be proportional to a Rayleigh number to maybe a quarter or maybe 0.3, but somewhere around 1/3 is not wrong. And what we would like to do is simply to verify this empirical relationship computationally with aspect. So what we're going to do is we're going to choose a certain set of parameters, namely rho naught, G, alpha, delta T, D, K, CP, and kappa in the following way. And we're going to play with the viscosity. So we keep the box and the boundary conditions and the temperature difference fixed. We're going to change the viscosity of the material. And by that, we're going to change the Rayleigh number. And then we're going to figure out for different values of the viscosity, so for different Rayleigh numbers, what heat flux do we get? And does it really follow this empirical relationship that the heat flux is proportional to the Rayleigh number, to the 1/3? So I'm going to show you this in a second in the virtual machine, but I want to also show you other things, how we can determine what the heat flux actually is. So Aspect is going to compute the heat flux through the bottom and the top boundaries in every time step and put it into an output file, into a statistics file. It's called output/statistics. You can open this with this CIG open command, and you can plot the properties that are listed in the statistics file as well. So if you wanted to plot this, you would get a plot like this. So in the beginning, heat flux is low. That's because convection has not yet started. But after some time, convection gets started, and then it sort of forms a steady state. And that's what we're going to use to visualize or to create this empirical relationship. What we're going to do at the end is that we ask you to just pick a particular Rayleigh number by choosing a particular viscosity and choose a particular refinement level. So how fine is the mesh? And then we're going to fill in a spreadsheet, and hopefully we're going to find the relationship that we were hoping for. So let me show you this in practice. So let me go over to my virtual machine over here. So I have, so this is the virtual machine, and let me make this full screen. So I have, I should start from the bottom, from the top. So when you start the virtual machine, it looks like this, okay? And Timo used the key shortcut. I'm going to open the terminal window by just clicking on this terminal emulator. A terminal is a program that provides you with a command line, okay? So I'm going to open this terminal window. I'm going to make it a little bit larger. I'm also going to make the font size a little bit larger by hitting Control+. Well, maybe not. Does not seem to work. Here we go. So if I want to see what's in my directory, in my home directory, it looks like this right now. And I've already entered this git clone command that Timo showed in the previous hour, where you can download the input file. So if I go into Aspect Tutorials, and then I list ls the content of this directory, there's a directory called 2020 Tectonics Modeling. So I go here. There is a day 1 directory in here, and it has this tutorial.prm. Okay, so if I type leafpad tutorials, tutorial.prm, you get to see exactly the file that we just talked about, right? With all of the input sections, like for the geometry model here. And like I said, later on, the parameters that we ask you to change is the initial global refinement that is listed here, and the viscosity, and the viscosity is given right here. Okay, so these are the 2 places that you will have to change. Let me close this. And then, so tilde corresponds to my home directory. In the home directory, there is a directory called aspect, and in this directory is an executable that is called aspect. And if I run this with tutorial.prm, so then you get exactly the output that Timo showed you before. So it's scrolling pretty quickly for me, but you probably only see a refresh every second or two. So let's see, we're making progress here. Okay, so here we are. So in my directory now is a new subdirectory output. So if I go into this here, that's where the statistics file is. Okay, so the statistics file, let me do this with XDG open. Statistics. Okay, it looks like this. So there's a description of the, so you can think of this as a spreadsheet, okay, with different columns and different rows, and here is a description of what in the different columns is. So in column number 1, you have the number of the time steps. It starts at 0, 1, 2, 3, and so on and so forth. Column number 2, you have the time. So this is, it starts at 0. The next one is at 4.9 billion years already. Get the idea. This is not a realistic benchmark in any regard. And then the time step size and so on and so forth. So what we're interested in is, in this case, the output heat flux through boundaries left, right, bottom, and top. Okay, and in particular, we're interested in the top and the bottom boundaries, and they are in columns 19 and 20. Okay, so what we're really interested in is the heat flux through the top and the bottom boundary, columns 19 and 20, in relation to the current time in column 2. And so the way you visualize this, well, there's many different ways. You can import it in Excel, for example, or in any other spreadsheet. But we're going to use a very simple program that's called GNU plot, the GNU plot. And it has a fairly simple syntax. So I can say I want to plot the input file, the statistics file, okay, using column 2, that was the time, and want to plot that against column 19, that was the bottom boundary, I believe, or maybe the top boundary. And it's going to look like this. So I can tell you it's the bottom boundary because the outward heat flux is negative. Okay, so that means that there is an inward heat flux, so that's the bottom boundary. And you see that in the beginning, not very much is happening, and then when convection starts, it starts to oscillate until it sort of finally finds some sort of steady state. I can plot this in many different ways. So let me get this a little bit arranged here. So I can say set style data lines, and then it's going to plot this not as individual points, but as a line. So I'm going to get this. And maybe I want to plot not only the bottom heat flux, but also the top heat flux. So I'm just going to add to it statistics using 2:20, okay? And it's going to look like this. So you see that the bottom and the top heat flux are sort of symmetric to each other. And I think that makes sense because at least in the long run, of course, the amount of heat that flows into the bottom boundary must also flow out of the top boundary, unless the box would permanently heat up or cool down. Okay, so you see that the negative heat flux at the end here is through the bottom is equal to the positive heat flux out of the top at the end here. And both of these are pretty much exactly equal 100,000. Okay, so if you let me make my window a little bit smaller again. If you go back to the program, it has a link here to a spreadsheet somewhere, and the spreadsheet looks like this. And in my case, I have chosen, I need to look this up again. So what was my quit. So my input parameters consisted of initial global refinement 3. So in the spreadsheet, I am here in this row, okay? And the viscosity that I had chosen was 5.1 times 10 to the 24. So 5.1 times 10 to the 24. So I'm here. And the heat flux that I had was pretty much exactly 100,000. Okay. I'm pretty sure this was correct, but let's double check this again. So I can go back into my output directory. I can call GNuplot again, and then I hit the key up, and it's going to allow me to repeat this. So maybe I should also just plot a constant just to see. So the blue line corresponds to 100,000. That's pretty much exactly what I have over here. And maybe I should choose a larger end time so that I can really be confident that this is the steady state limit and not just what I happen to get. But for the moment, this is good enough, I would say. So maybe I need to have a larger end time. But so I filled in this here. And if you all for the next 20 minutes or so want to repeat these steps and take one of these spots here, so just put your initials in there or a name, and then when you have the end result, replace your name by a number, then hopefully by the end of this hour, we should have data points that correspond to 2, 3, and 4 global mesh refinements, or if you have a fast computer and a lot of patients, then you can also choose 5, that hopefully will reproduce this empirical relationship that the heat flux is proportional to the Rayleigh number to the 1/3. So I think this is a good place to stop. I think this is what we wanted to show. And let's take a 15-minute break, maybe. It is now 8 minutes past the hour, so I would say let's meet again at, Timo, what do you think? 20 past or 25 past?
Let's do 25 past.
Okay, let's meet at 25 past for all normal time zones and 55 past for India time zone, and see where we are. And I'm going to keep sharing the spreadsheet, and if people want to fill in individual data points, then hopefully this fills in over time. I'll see you in about 15 minutes.